All right, put yourself right in the driver's seat for your upcoming networking exam. Today, we're basically going to create the ultimate cheat sheet to entirely demystify the data link layer. If you've been, staring at textbook pages until your eyes cross, you are absolutely in the right place. We're going to break this all down logically so it actually sticks.
So, ready to ace those Layer 2 questions? Let's just dive right into this explainer. I really want you to frame networking not as some dense, boring textbook chapter, but rather as a series of chaotic, messy problems that Layer 2 heroically steps in to solve. I mean, sending raw digital information across a wire is incredibly messy, and without the data link layer, it would literally be absolute pandemonium.
Here is our game plan for today. We're covering context with the OSI model, the 2 DLL sublayers, the 4 core DLL functions, methods of framing, and finally, flow and error control.
Okay, let's kick things off with Section 1, Context in the OSI model.
Think about exactly where Layer 2 lives in the grand scheme of things. It sits directly between the physical layer, right at the bottom, and the network layer just above it. It's this critical bridge, because you see, the physical layer just blindly handles raw, unstructured electrical or optical bits. It doesn't know what they mean. And the network layer, that handles routing packets across entirely different networks. So the data link layer, right in the middle, has one huge job: node-to-node delivery. It makes sure that raw data transfer is synchronized and entirely error-free across that specific physical link.
Moving right along to Section 2, the 2 DLL sublayers. You can really think of these 2 sublayers working together like a highly coordinated team. The Logical Link Control, or LLC, is essentially the brain of the operation. It deals with the high-level stuff: multiplexing, managing the flow of data among applications, and spitting out error messages and acknowledgments. Beneath that, you've got the Media Access Control, or MAC sublayer. This is the muscle. It handles the gritty, physical hardware interaction, controls actual access to the media, and takes care of addressing the frames themselves.
All right, Section 3, the 4 core DLL functions.
If you memorize anything for the test, make it this master list. These are the 4 specific solutions to the chaos of a physical wire: framing, addressing, error control, and flow control. Let's break these down one by one, starting with framing.
So how do you actually solve the problem of knowing where a piece of data begins and ends? Well, we use framing. The data link layer receives packets from the network layer above, and it divides them into smaller, readable blocks of information called frames. It's basically packaging up all those unstructured ones and zeros into organized, discernible chunks before tossing them bit by bit down to the physical layer.
Next up, addressing. This literally solves the problem of who is who on a local network. Every single device gets assigned a unique hardware address, yep, the MAC address, right during manufacturing. Think of it as a permanent fingerprint for the device. It ensures that when a frame is zipping across the local network, it actually gets delivered accurately from one specific node to the exact right destination.
Our third function is error control. Real-world environmental noise, like electromagnetic interference, can seriously scramble your data on the physical wire. Error control is basically the network's guard dog. It detects if bits have been corrupted or duplicated during transmission, and it takes immediate action to correct it, usually by just dropping that bad frame and demanding a fresh copy.
And finally, flow control. Think of flow control like trying to slow down a really fast talker so a slow listener can actually write down everything being said without missing a single word. If a powerful sender just blasts frames faster than a slower receiver can process them, the receiver's buffer overflows and poof, frames get lost. Flow control steps in to prevent that massive traffic jam. Let's move into Section 4, Methods of Framing.
So, when we talk about a frame, we're really talking about a sandwich. The data link layer takes that data packet from the network layer and sandwiches it right between a brand new header and trailer. The header holds all the crucial control info, like the destination and source MAC addresses, while that trailer at the end typically holds the error detection information we just talked about.
Now, a super important distinction to keep in mind for the exam is how the receiving computer actually spots the start and end of that frame. There are 4 specific methods you need to know. You've got character count, which simply states the total number of characters right up front. Then character stuffing and bit stuffing. These cleverly insert special escape flags or extra bits to clearly mark boundaries without confusing the actual payload data. And lastly, physical layer coding violations, which use intentional redundancies in the physical signal itself to mark where the frame begins and ends.
Finally, that brings us to Section 5, Flow and Error Control.
Okay, let's tackle flow control first.
You've basically got two main strategies to pull this off. You can control data flow using a feedback-based system, which literally means waiting for the receiver to send back a thumbs-up permission before sending more data. Or you can use a rate-based system. This just enforces a strict, built-in speed limit on the sender, entirely eliminating the need to wait for feedback from the receiver.
When you look at how protocols have evolved, it's pretty fascinating. You start with the simplest protocol, which honestly just assumes a fantasy, completely noiseless channel where the sender fires data continuously without a care in the world. But then you contrast that with the much more realistic stop-and-wait protocol. Here, the sender transmits one single frame and literally stops and waits. It requires an acknowledgement frame, an ACK, from the receiver before it is ever allowed to send the next piece of data.
But listen, real-world networks aren't just prone to traffic jams. They are incredibly noisy. Frames are going to get lost or corrupted, for sure. Because of this, engineers cleverly combine flow and error control into what we call ARQ protocols, or automatic repeat request. These automatically request a retransmission if frames get damaged. The top three you absolutely need to know are stop-and-wait ARQ, go-back-in ARQ, and selective repeat ARQ.
Let's just boil this stop-and-wait ARQ sequence down to 4 easy steps for your test. First, the sender transmits a frame and immediately starts a countdown timer. Second, it smartly keeps a copy of that frame in its own memory. Third, the receiver checks the frame. If it's clean, it sends back an acknowledgement. And fourth, this is where the magic happens. If the sender's timer expires before that ACK ever arrives, it just assumes the frame was lost or corrupted and uses its saved copy to retransmit. It's a brilliant way to guarantee delivery even when the channel drops your data.
And hey, if your exam brings up access control for wired Ethernet setups, you absolutely have to remember CSMA/CD, Carrier Sense Multiple Access with Collision Detection. When multiple devices share one channel, collisions are going to happen. This protocol solves it. A station listens to the wire. If it sends a frame and detects a collision, it blasts a jamming signal to warn everyone, and then, this is the critical part, it waits a random back-off time before trying again. That random timer is what prevents all the devices from just colliding endlessly all over again.
Okay, I'm going to leave you with a final thought to really test your knowledge before exam day. Let's say your receiver is dropping packets because it is simply too slow to process the incoming stream. Which specific data link layer function has failed? Think back to our 4 core functions. Ask yourself, does this scenario describe a failure to detect corrupted bits, or is it an inability to pump the brakes on a fast sender? Figure out that distinction and you will absolutely ace this topic. Good luck studying, you've totally got this.